Linear programming and routing, an application to Vertex cover. We will start by introducing a powerful technique from operations research, linear programming. Linear programming is the subject of entire courses, and we will not attempt to provide any kind of a comprehensive overview of it here. In this section, we will introduce some of the basic ideas underlying linear programming and show how these can be used to approximate NP-hard optimization problems. Recall that in section 11.4, we developed a two-approximation algorithm for the weighted vertex cover problem. As a first application for the linear programming techniques, we will give here a different two-approximation algorithm that is conceptually much simpler, though slower in running time. Linear programming as a general technique. Our two-approximation algorithm for the weighted version of a vertex cover will be based on linear programming. We describe the linear programming here not just to give the approximation algorithm, but also to illustrate its power as a very general technique. So what is a linear programming? To answer this, it helps to first recall from linear algebra the problem of simultaneous linear equations. Using matrix vector notation, we have a vector x of unknown real numbers, a given matrix A, and a given vector B, and we want to solve the equation Ax equals to B. Gaussian elimination is a well-known efficient algorithm for this problem. The basic linear programming problem can be viewed as a more complex version of this, with the inequalities in place of equations. Specifically, consider the problem of determining a vector x that satisfies Ax which is greater than or equals to B. By this notation, we mean that each coordinate of the vector Ax should be greater than or equal to the corresponding coordinate of the vector B. Such systems of inequalities define regions in space. For example, suppose x equals to x1, x2 is a two-dimensional vector, and we have the four inequalities. x1 which is greater than or equals to 0, x2 which is greater than or equals to 0, x1 plus 2x2 is greater than or equals to 6, and the 2x1 plus x2 is greater than or equals to 6. Then the set of solutions is the region in the plane shown in figure 11.10. Given a region defined by Ax which is greater than or equals to B, linear programming seeks to minimize a linear combination of the coordinates of x over all x belonging to the region. Such a linear combination can be written C transpose times x, where C is a vector of coefficients and C transpose times x denotes the inner product of the two vectors. Thus, our standard form for linear programming as an optimization problem will be the following. Given n by n matrix A, and the vectors B, which is in R to the n, and C, which is in R to the n, find a vector x in R to the n to solve the following optimization problem. That is, we want to minimize C transpose times x such that x which is greater than or equals to 0 and Ax which is greater than or equals to B. C transpose x is often called the objective function of the linear program, and Ax greater than or equals to B is called the set of constraints. For example, suppose we define the vector C to be 1.51 in the example in figure 11.10. In other words, we are seeking to minimize the quantity 1.5 x1 plus x2 over the region defined by the inequalities. The solution to this would be to choose the point x equals to 2, 2, where the two slant lines cross. This yields a vector of C transpose times x equals to 5, and one can check that there is no way to get a smaller value. We can phrase linear programming as a decision problem in the following way. Given a matrix A, vectors B and C, and a bound gamma, thus there exists x so that x is greater than or equals to 0, Ax is greater than or equals to B, and C transpose times x is less than or equals to gamma. To avoid issues related to how we represent real numbers, we will assume that the coordinates of the vectors and matrices involved are integers. The computational complexity of linear programming. The decision version of linear programming is in NP. This is intuitively very believable, We just have to exhibit a vector x satisfying the desired properties. The one concern is that even if all the input numbers are integers, such a vector x may not have integer coordinates, and it may in fact require very large precision to specify. How do we know that we'll be able to read and manipulate it in polynomial time? But in fact, one can show that if there is a solution, then there is one that is rational and needs only a polynomial number of bits to write down, so this is not a problem. Linear programming was also known to be in CoMP for a long time, though this is not as easy to see. Students who have taken a linear programming course may notice that this fact follows from linear programming duality. For a long time, indeed, linear programming was the most famous example of a problem in both MP and CoMP that was not known to have a polynomial time solution. Then in 1981, Leonid Khachiyan, who at the time was a young researcher in the Soviet Union, gave a polynomial time algorithm for the problem. After some initial concern in the US popular press that this discovery might turn out to be a Sputnik-like event in the Cold War, it didn't. Researchers settled down to understand exactly what Khachiyan had done. His initial algorithm, while polynomial time, was in fact quite slow and impractical. But since then, practical polynomial time algorithms, so-called interior point methods, have also been developed, following the work of Narendra Karmarkar in 1984. Linear programming is an interesting example for another reason as well. The most widely used algorithm for this problem is the simplex method. It works very well in practice and is competitive with polynomial time interior methods on real-world problems. Yet its worst-case running time is known to be exponential. It is simply that this exponential behavior shows up in practice only very rarely. For all these reasons, linear programming has been a very useful and important example for thinking about the limits of polynomial time as a formal definition of efficiency. For our purposes here, though, the point is that linear programming problems can be solved in polynomial time, and very efficient algorithms exist in practice. You can learn a lot more about all this in course on linear programming. The question we ask here is this: how can linear programming help us when we want to solve combinatorial problems such as vertex cover? Vertex cover as an integer program. Recall that a vertex cover in a graph G equals to VE is a set S which is a subset equals to V, so that each H has at least one end in S. In the weighted vertex cover problem, each vertex I in V has a weight Wi which is greater than or equals to 0, with the weight of a set S of vertices denoted W of S is equal to the summations of Wi summing for all I in S. We would like to find a vertex cover S for which W of S is a minimum. We now try to formulate a linear program that is in close correspondence with the vertex cover problem. Thus, we consider a graph G equals to VE with a weight Wi which is greater than or equals to 0 on each node I. Linear programming is based on the use of vectors of variables. In our case, we will have a decision variable xi for each node I in V to model the choice of whether to include the node I in the vertex cover. Xi equals to 0 will indicate that the node I is not in the vertex cover, and xi equals to 1 will indicate that the node I is in the vertex cover. We can create a single n-dimensional vector x in which the nth coordinate corresponds to the coordinate corresponds to the ith decision variable xi. We use linear inequalities to encode the requirement that the selected nodes form a vertex cover. We use the objective function to encode the goal of minimizing the total weight. For each h I, j, and e, it must have one end in the vertex cover, and we write this as the inequality xi plus xj, which is greater than or equals to 1. Finally, to express the minimization problem, we write the set of node weights as an n-dimensional vector w with the ith coordinate corresponding to wi. We then seek to minimize w transpose times x. In summary, we have formulated the vertex cover problem as follows. VC.ip is to minimize the summations of wi times xi summing for all I in V such that xi plus xj is greater than equals to 1 xj is greater than equals to 1 for all ij in E, and the xi is chosen among the set either 0 or 1.
We claim that the vertex covers of G are in one-to-one correspondence
the vertex covers of G are in a one-to-one correspondence with the solutions X
in which
to
all
this
coordinates
system
are
of linear
equal to 0
inequalities
or
in
1.
which all coordinates are equal to 0 or 1.
S is a vertex cover in G if and only if the vertex
S is a vertex cover in G if and only if the vertex, the vector x defined as xi equals to 1 for I in S and xi equals to 0 for I not in S satisfies the constraints in VC.ip. Further, we have a W of S equals to W transpose times X. We can put this system into the matrix form we used for linear programming as follows. We define a matrix A whose columns correspond to the nodes in V and whose rows correspond to the edges in E. Entry A of EI equals to 1 if node I is an end of the edge E and 0 otherwise. Note that each row has exactly 2 non-zero entries. If we use 1 arrow to denote the vector with all coordinates equal to 1 and 0 arrow to denote the vector with all coordinates equal to 0, then the system of inequalities above can be written as ax is greater than or equals to 1 and 1 is greater than or equals to x, which is greater than or equals to 0. But keep in mind that this is not just an instance of the linear programming problem. We have crucially required that all coordinates in the solution be either 0 or 1. So our formulation suggests that we should solve the problem. The minimizations of W transpose times X subjected to 1 which is greater than or equals to X, which is greater than or equals to 0, and AX is greater than or equals to 1. For X has integer coordinates. This is an instance of the linear programming problem in which we require the coordinates of X to take integer values. Without this extra constraint, the coordinates of X could be arbitrarily real numbers. We call this problem integer programming as we are looking for integer valued solutions to a linear program. Integer programming is considerably harder than linear programming. Indeed, our discussion really constitutes a reduction from vertex cover to the decision version of integer programming. In other words, we have proved that 11.22 vertex cover is polynomial time reducible to integer programming. To show the NP completeness of integer programming, we would still have to establish that the decision version is in NP. There is a complication here, as with linear programming, since we need to establish that there is always a solution X that can be written using a polynomial number of bits. But this can indeed be proven. Of course, for our purposes, the integer program we are dealing with is explicitly constrained to have solutions in which each coordinate is either 0 or 1. Thus, it is clearly in NP, and our reduction from vertex cover establishes that even this special case is NP complete. Using linear programming for vertex cover, we have yet to resolve whether our foray into linear and integer programming will turn out to be useful or simply a dead end. Trying to solve the integer programming problem VC.ip optimally is clearly not the right way to go, as this is NP hard. The way to make progress is to exploit the fact that linear programming is not as hard as integer programming. Suppose we take VC.ip and modify it, dropping the requirement that each xi is in the set among 0 and 1 and reverting to the constraint that each xi is an arbitrary real number between 0 and 1. This gives us an instance of the linear programming problem that we could call vc.lp, and we can solve it in polynomial time. We can find a set of variables, the set xi star between 0 and 1, so that xi star plus xj star is greater than or equals to 1 for each age ij, and the summations of wi times xi star summing for all index I is minimized. Let x star denote this factor, and the WLP is equals to W transpose times x star denote the value of the objective function. We note the following basic fact. 11.23. Let S star denote a vertex cover of a minimal weight, then WLP is less than or equals to W of S star. Proof vertex covers of G correspond to integer solutions of VC.IP, so the minimum of mean of W transpose times X such that 1 is greater than or equals to X, which is greater than or equals to 0, and Ax is greater than or equals to 1 over all integer X vectors is exactly the minimal weight vertex cover. To get the minima of the linear program VC.LP, we allow X to take arbitrary real number values. That is, we minimize over many more choices of X, and so the minima of VC.LP is no larger than that of VC.IP. Note that 11.23 is one of the crucial ingredients we need for an approximation algorithm, a good lower bound on the optimum in the form of the efficiently computable quantity, WLP. However, WLP can definitely be smaller than W of S star. For example, if the graph G is a triangle and all weights are 1, then the minimal vertex cover has a weight of 2. But in a linear programming solution, we can set xi equals to 1/2 for all 3 vertices, and so get a linear programming solution of weight only 3 divided by 2. As a more general example, consider a graph on n nodes in which each pair of nodes is connected by an edge. Again, all weights are 1. Then the minimal vertex cover has weight n-1, but we can find a linear programming solution of value n over 2 by setting xi equals to 1/2 for all vertices I. So the question is, how can solving this linear programming help us actually find a near optimal vertex cover? The idea is to work with the values xi star and to infer a vertex cover S from them. It is natural if xi star is equals to 1 for some node I, then we should put it in the vertex cover S. And if xi star is equals to 0, then we should leave it out of S. But what should we do with the fractional values in between? What should we do if xi star is equals to .4 and xi star is equals to .5? The natural approach here is to round. Given a fractional solution, the set of xi star, we define S is equals to the set of index I in V such that xi star is greater than or equals to 1/2. That is, we round values at least 1/2 up, and those below 1/2 down. 11.24. The set S defined in this way by rounding is a vertex cover, and the weight of S is less than or equals to WLP. Proof. First, we argue that S is a vertex cover. Consider an edge E equals to ij. We claim that at least one of I and j must be in S. Recall that one of our inequalities is xi plus xj, which is greater than or equals to 1. So in any solution x star that satisfies this inequality, either xi star is greater than or equals to 1/2 or xj star is greater than or equals to 1/2. Thus, at least one of these two will be rounded up, and I or j will be placed in S. Now we consider the weight W of S of this vertex cover. The set S only has vertices with xi star, which is greater than or equals to 1/2. Thus, the linear program paid at least 1/2 times Wi for node I, and we only pay Wi at most twice as much. More formally, we have the following chain of inequalities. That is WLP times W transpose times X star is equal to the summations of Wi times Xi star, summing for all index I, which is greater than or equal to the summations of Wi times Xi star, summing for all index I, which is in S, which is greater than or equal to 1/2 times the summations of Wi, summing for all I in S, which is equal to 1/2 times W of S. So it's a two approximation. Thus, we have produced a vertex cover S of weight at most 2 times WLP. The lower bound in 11.23 showed that the optimal vertex cover has weight at least WLP, and so we have the following result. 11.25. The algorithm produces a vertex cover S of at most twice the minimum possible weight.